Good afternoon, dear colleagues. To your attention is offered a report on the topic on the use of gray codes for solving 0 to 1 combinatorial problems of optimization and decision-making in environmental and economic systems. Environmental and economic problems are an example of a complex of tasks, the solution of which is associated with high costs. And the decisions themselves have a long-term, large-term impact on the fate of large social groups. Any ecological and economic system is a complex, weakly deterministic and evolving research object. The choice of strategies for making environmental and economic decisions in such large-scale systems is associated with the analysis of a huge number of factors, relations and interests. This leads to the need of use of modern means of analysis. Forecasting and mathematical modeling of the behavior of complex systems based on the information and computer technologies and decision support systems. The foundations of mathematical modeling of complex ecosystems were developed by such scientists as V. Volterra, V. G. Zaslavsky, A. N. Kolmogorov, G. I. Marchuk, U. Odom, R. A. Poluektov, U. M. Svarezhev. A great contribution to the study of environmental and economic problems of environmental management was contributed by such scientists as O. F. Balatsky, K. G. Goffman, V. I. Gurman, A. V. Letov, V. V. Leontiev, N. N. Olenev, A. A. Petrov, I. G. Pospelov, R. L. Ryatskas, G. A. Ugolnitsky, and others. Among the Ukrainian scientists it should be noted the works of A. A. Bakareva, A. P. Velikogo, V. M. Hayetsa, V. M. Glushkova, V. S. Grigokiva, U. M. Ermolyeva, S. I. Dorogantsova, A. G. Avaknenko, V. S. Mikhailovicha, B. N. Pasheniknogo, N. Z. Shora. Despite the deep scientific developments, the processes of environmental and economic cooperation require further study in order to develop new and improving the already existing methods for solving socio-economic problems and conservation of natural resource potential. The results of mathematical modeling of the scheme of an ecologically balanced economy of individual regions, and, in particular, their dynamic optimal development, can serve as a basis for making management decisions aimed at improving the efficiency of environmental and economic systems. The tasks of the Boolean programming are played an important role in the study of these systems, and are the class of problems of discrete optimization, which are widely used at solving the problems of making schedules and destination, investment planning and placement of enterprises and the nodes of communication networks, unification and standardization and etc. As a target function in these problems use either the amount of total costs for the creation and operation of the system, or the total system efficiency, the amount of work performed. Numerous monographs, see works 1 to 6, and articles, see for example 7 to 12, are devoted to studying the problems of Boolean programming. Despite the simplicity of the wording of such tasks, most of them belong to the class of NP-hard problems, see 13. Among the most popular methods for solving a problems of Boolean programming it is possible to allocate exact methods, branch and bound method and dynamic programming and their combination, approximate algorithms with a guaranteed deviation, evolutionary, genetic algorithms, ant colonies optimization, and meta-heuristic algorithms, simulated annealing, taboo search, greedy randomized adaptive search procedure, GRASP, variable neighborhood search and etc. In practice, the solution of these tasks requires large computational costs, which substantiates the feasibility of applying various ways to reduce the dimension of the problem. For example, using to reduction of source optimization problem to a problem of optimize the corresponding pseudo-Boolean function. Recall that the real functions defined on the set of Boolean variables, by analogy with the Boolean functions, are called pseudo-Boolean. See works 14 to 17. Accordingly, the problems of optimization of pseudo-Boolean functions are called the problems of pseudo-Boolean optimization. Any pseudo-Boolean function can be the only way presented as a multi-polynomial type. In addition, any pseudo-Boolean function can be represented as, if bk0, then the second expression is the Parsi form of the function f. Any pseudo-Boolean function can be recorded as the Parsi form. The formal statement of the problem of conditional pseudo-Boolean optimization is as follows. Many problems in environmental and economic systems lead to the need to solve conventional optimization problems with Boolean variables. Another important feature in solving combinatorial problems with Boolean variables is to use gray codes and parallel calculations to reduce the time of recalculation of the objective functions and restrictions in various schemes of branching the decisive algorithm, for example, the method of branches, borders and cutting, dynamic programming, etc. The paper discusses the use of binary reflected gray codes to solve combinatorial problems with pseudo-Boolean functions, polynomials from Boolean variables. The recursive G-Ehrlich algorithm is given for generate a sequence of strings n discharge gray codes, in which each next string differs from the previous one by one discharge bit. On the examples of the solution of the 0 to 1 knapsack problems, see work 18, and the problems of choosing the capacity of arcs with constraint on flow delay time, see work 19. It is shown how these codes can be used to effectively calculate the values of the target function and restrictions. The purpose of the article is to show the developers of algorithms and programs how to apply gray codes in various branching schemes of the decision algorithm. For example, in the branch and bound method, when the number of binary, Boolean, variables at the nodes of the tree is small, less than 35. The research methodology is based on a computational experiment for solving the above problems with the proposed algorithm of exhaustive search of the solution with partial and full recalculation of the values of objective function and constraint of the problem. During the experiment, the accuracy of solving the 0 to 1 knapsack problem by a greedy, heuristic algorithm was also checked. The mathematical formulation of the first problem is as follows. The second problem is to choose an arc's capacity from a given set of discrete integer values when limited to the maximum flow delay time, which is relevant for the distribution flows in multi-commodity communication networks. In this problem, delays of flows TKL on arcs are defined as, and the constraint on the delay time of flows TAV in a network has the following form. Here FKL, fixed arc flow value, E, set of arcs of network, WKL, bandwidth capacity of arc, Tmax, the maximum of flows delay time in network, U, total flow in network, Uij, value of the flow from a node I to a node J, S, set of pairs of indexes corresponding nodes in the network. We consider a direct connected network G with a set of nodes N, and a set of arcs E in network for each direct arc KL, exist back arc LK. The arc represents a switched communication line in a data network or a vehicle route, the final nodes of which coincide with the initial and final node of the arc. The network may contain loops and parallel arcs, since cyclic and repeating communication lines and communication lines with the same final nodes are allowed. An integer flow matrix is given on the network U. Let WKL sort for a bandwidth capacity of arcs of the network in transport blocks WKL, ascending positive integers, DKL, arcs lengths. CKL, discrete values cost of arcs, FKL, fixed total flows in transport blocks, are flowing along the arcs of the network, where UIJKL is the flow of transport blocks from I to J, which passes along arc KL. It is required to find the minimum value of the network cost function. Note that problem 4.5 can be represented as a knapsack problem with Boolean variables and multi-choice, 0 to 1 multiple-choice knapsack problem, 0 to 1 MCKP. Let Cij, discrete values cost of arcs I with capacity Wij and length di, Tij, delays of flows on arcs, phi, flow on the arc I. Suppose that Xij equals 1 if for the arc I the capacity Wij is selected, and Xij equals 0 otherwise. We require to find, here, the required throughputs correspond to the optimal solution to the problem. 6.9. It is easy to see that any individual problem formulated in the form of 4.5 can be transformed into the corresponding instance of problem 6.9. To do this, it is necessary to construct two matrices whose rows correspond to arcs, the columns, to a set of discrete capacities, and the cost of arcs and delays on arcs are taken as matrix elements. The converse is also true. In 19, it has been proven that the optimization problem formulated in the form 4.5 is NP-hard. And for its solution, two approximate algorithms were proposed on the basis of the approximation of discrete cost functions by linear ones, and on the method of sequential analysis of options. The first algorithm uses the Lagrange multiplier method, which allows one to analytically solve a relaxed problem and obtain an exact continuous solution. The second algorithm enumerates the solutions, narrowing the range of feasible solutions at each iteration, and can be used for any monotonically non-decreasing cost of arcs with an increase in their throughput. It can be applied both to the initial statement of the problem and to the statement in the form 6.9. It was shown that both algorithms at the final stage of work narrow the area of permissible solutions up to 2 values, and with complete full search variance allow us to obtain an exact solution. We write the abbreviated problem in the form Problem 10.13 can be converted to 0 to 1 knapsack problem. All formulated problem are NP-hard, therefore there are no exact polynomial algorithms to solve them. See work 13. In books 1.5, you can find a description of the 3 exact pseudo-polynomial algorithms for solving problems 1, 3, and 14, 16. Based on the methods of branches and bounds and dynamic programming with using Lagrangian and LP relaxation. The programs listing of these algorithms, ExpressNap, MinApp and Combo, on C++ are shown on the dpassenger page on the Internet. In the same books, there are also completely polynomial approximate schemes for solving 0 to 1 kp problem, FPTAS, fully polynomial time approximation scheme. This means that for them there are algorithms that polynomial time of the size for the input of the problem make it possible to obtain a guaranteed approximate solution for maximization or minimization problem, respectively, where epsilon is an arbitrarily small positive number. For a complete enumeration of options for solving problems 1, 3, and 14, 16, we will use the algorithm for generating a sequence of binary reflected n-digit gray codes proposed by Ehrlich in 26. The algorithm makes it possible to efficiently calculate the values of the objective function 1 or 14 and constraints 2 or 15 during the solution process. Binary mirrored, reflective, gray code is defined according to the following recursive rules. Tth n-bit gray code is an ordered cyclic sequence of n-bit strings, in which successive strings differ only by 1 bit. In exhaustive search algorithms for calculating the values of various functions using gray codes, it is convenient to represent these codes as an ordered list of bit numbers that change their value to the opposite when moving from the current line to the next. This sequence of transitions Pn can be determined by the following recursive rules. It is interesting to note that if we construct a graph whose vertices correspond to binary sequences of length n, and the edges connect two vertices that differ only by 1 digit, then such a graph represents a binary n-dimensional cube. Moreover, the constructed binary sequence corresponds to a Hamiltonian path in such a graph. To generate a sequence of transitions Pn in a binary string, we define a vector of pointers, which simulates a stack for recursive definition of Pn. The optimal solution will be saved in a vector. OPT1 algorithm with partial recalculation of the objective function and constraints for problem 1, 3. In the variant of solving the problem with a complete recalculation of the objective function and constraint, OPT2 algorithm, step 1 and step 5 will be replaced by. For an algorithm with partial recalculation of the objective function and constraints for problem 14, 16, the pseudocode will be as follows. Comparison of the performance of algorithms OPT1 and OPT2 was carried out for problems 1, 3, and 14, 16, using examples generated by a pseudo-random number generator. Here, the results of the solution are given only for problem 1, 3, since data similar in characteristics were obtained for problem 14, 16. For all dimensions of the problem 1, 3, which varied from n equals 5 to n equals 36, the cost of items and their weight were generated in the range from 5 to 10 and from 1 to 20, respectively. During the experiment, the accuracy of solving problem 1, 3 by the greedy, heuristic algorithm OPT3 was also checked. The algorithm is based on the preliminary of ordering of items on not increasing their specific costs in a given set with followed by the choice of items in knapsack until a restriction on size the knapsack is well known. See for example 5.27, that solutions OPT3 obtained by the greedy algorithm may differ from the optimal no more than twice when choosing the final cost of the knapsack from the condition, where max C is the maximum cost of the item in the specified set. In Figure 1 shows the time to solve problem 1, 3 with an accuracy of 2 signs after the comma, on the PC with a clock frequency 2.66 GHz for OPT1 and OPT2 algorithms with partial and complete recalculation of the target function and restrictions. As can be seen from Figure 1, OPT1 algorithm can be used for practical calculations in branching schemes when the number of variables in branching nodes does not exceed 35. Calculation time at n equals 35 is about 8 minutes. OPT1 algorithm for variance 5 to 10 is faster than OPT2 algorithm on average in 7 times. In Figure 2 shows the results of the solution of problem 1, 3, with an exact OPT1 algorithm and the greedy algorithm OPT3. The results of solutions of the OPT1 and OPT2 algorithms, of course, coincide. Values ASUM-OPT are shown for OPT1 algorithm. The values of the target function obtained by the greedy algorithm differ from the optimal within del% from 0 to 12.5%. The OPT3 algorithm has a polynomial estimate of time complexity and can be applied in practice to solve problems 1, 3 of a large dimension. One needs to quickly get the approximate value of the target function with limited computing resources. For example, the problem 1, 3 was solved for n equals 10,000 with the same boundaries of changes in values c and I in 0.11 seconds. In this case, OPT3 equals 70,598, ASUM-OPT equals 103,985 at W equals 104,000. All programs are written in the Fortran language in the Microsoft Developer Visual Studio environment and can be adapted to work in the parallel programming system Intel Parallel Studio XE 2020 in which are included the latest versions of C, C++ and Fortran compilers. Application of binary reflected, mirror, reflexive, gray codes to solve combinatorial problems with pseudo-Boolean functions, polynomials from Boolean variables, is considered. A recursive Ehrlich algorithm is given for generating a sequence of lines n-bit gray codes, in which each next line differs from the previous one by only 1 bit. On example of the 0 to 1 knapsack problem is shown how these codes can be used to efficiently compute the values of the objective function and constraints. The purpose of the article is to show the developers of algorithms and programs how to apply gray codes in various branching schemes of the decision algorithm. For example, in the branch and bound method, when the number of binary, Boolean, variables at the nodes of the tree is small, less than 35. The research methodology is based on a computational experiment for solving the 0 to 1 knapsack problem with the proposed algorithm of exhaustive search, the solution with partial and full recalculation of the values of objective function and constraint of the problem. During the experiment, the accuracy of solving the problem by a greedy, heuristic algorithm was also checked. As a result of the experiment, it was found that the algorithm with a partial recalculation of the objective function and restrictions can be used for practical calculations in branching schemes. When the number of variables in the nodes of the branching tree does not exceed 35, the algorithm with partial recalculation is faster than the algorithm with full recalculation on average by 7 times. The heuristic, greedy algorithm can be applied in practice to solve the 0 to 1 problem of a knapsack of large dimension, more than 10,000 items. When need to obtain an approximate value of the objective function at the limited computing resources. The novelty of the work lies in the proposed approach to solving combinatorial optimization problems with pseudo-Boolean functions using gray codes. The efficiency of the proposed algorithm with a partial recalculation of the values of the objective function and constraints is shown. And it can be applied in practice in various branching schemes of the decision algorithm. Thanks for your attention.